Okay, so we will continue where we left off yesterday. So today we will set up the theoretical framework for understanding cosmology. Of course, it is a very wide subject, and so I will cover only some points that I feel is important, and the rest you will have to fill in, just to get you excited so that you can read up later on your own. Okay. So, I left yesterday by starting with the observations and setting up our dynamical variables that we are going to track. So, one of the first was the CMB temperature. So, this T variable is defined on the surface of a sphere because it is in the direction, and in general it will, whatever we measure today is what we measure today. But if it were we had measured it in the past, it would have been dependent on time. So, this is the variable we want to track. Then the matter density also, that is because of our measurement we look in some direction, maybe a volume in space in this side, and we assign coordinates to that region in space. To that coordinate in space, and then so the density is what we want to track, and we want to know how it changes as a function of space and time. And the I index here is going to represent the different components, whatever components are there in the universe. And we also introduced the scale factor, the rate not the rate, but the distance measurement between 2 points. If it changes at a later time, the change is captured by this variable A, which will change as a function of time. And we will also be interested in all this story in the values that we measure today. So, we usually in the literature, if you find a 0 or not symbol attached, that means it is measured at t equal to t naught, which is today. Okay. T naught, and similarly for the density, and similarly for the scale factor. So, by convention, what I explained to you yesterday, you should have understood that when we say distance, what is the distance at this time? There is no, the t A is not a very well defined at any time t. What is the value of t? A is not very well defined. What is well defined is the ratio at a particular time and a later time or past time. So, between two times, the length, comparison of the length is what is meaningful. And so, usually what people do is we take A0, the scale factor today, as 1, and then if the universe is expanding, back in the past it would have been, the value would have been less than 1. Excuse me, why what is so funny?
What is the time here, in which coordinates is this?
I will come to that. So, we are going to talk about cosmic time, and so that means we have to set up a coordinate system in which we are doing all these things. Okay. Okay. So, then in the last class I also talked about taking the average quantity of T and rho and perturbing about the average quantity. So, we are interested in following the average quantity and the perturbed quantity. So, and that is done by using perturbation theory. And you will notice that in the scale factor I have only one variable, scale factor A. This is coming from how we measure distance, and this also should be, there should be x dependent. You may ask, why is there no x dependence on this when these things have x dependence. So, we will see why I am writing here without any x dependence. So, we are interested in the question of why is space expanding, and we know that Newtonian physics does not, the theory is not capable of predicting any such thing. There is no dynamics for space. So, we have to go to general theory of relativity. So, what I am going to do in this coming lecture is to set up the dynamical equations for the, basically I will be interested in the average quantities, okay. But I will mention briefly about the perturbation also. So, I am supposed to give you the background evolution. So, but the word background, it typically means the averages, average quantities, they are called the background, and the perturbation on top of them are the fluctuations. Okay. So, we are going to set up those equations, and in some simple cases I will just tell you the solutions. By solution I mean solutions for these quantities. I will not be doing T because that is far more complicated, perturbations and so on. And then I will introduce the what we call as the standard cosmology, lambda CDM cosmology. This is what we will do. Okay. Okay. So, you had lectures on general relativity. So, I will do quick recap of the things that the essential points that I need for my purpose. Okay. So, let's start with Newtonian gravity. So, in Newtonian gravity I have already said space is not important, it just gives the locations, and also we do not have a limit on how, there is no speed limit on how material can travel. And the interactions between different bodies which have mass, we have the force law, which is the Newton's force law, the force is attractive. Then when we have a mass distribution in space, not just individual single objects, we describe the system by the gravitational potential phi is the gravitational potential. This will vary from place to place, and on the left hand side we have the gravitational potential, which is the second derivative Laplacian, and on the right hand side we have the density matter. So, this is the Poisson equation which you would have all solved and so on for example cases, and so this is the important equation that we want to see how does it generalize. Then we also have the conservation equation, energy conservation, the rate at which the rho changes with time is related to the divergence of this quantity, and so this is usually called the continuity equation. So, these are some of the, of course there are more equations, I am just summarizing the essential ones which we will see. Now, if you stare at this equation, you would have all heard that general relativity tells curve space time, matter tells it how to curve. So, if you look at this equation, can you foresee something that will come out from here? You have rho energy density on the right hand side, on the left hand side you have gravitational potential. So, if you sort of predate what GR will tell you, you may think that okay, this will enter into the GR equations, this phi will enter into the curvature of space time, okay, and that is what we will see now. Oh, okay. So, to go to GR from Newtonian physics, you would have learnt in the last two lectures that what we mean by distance on a flat space. On flat space we define distances as it is an invariant quantity under rotations, okay, on the 3-dimensional space, and if I have set up coordinates, then the distance between two objects, 2 points is invariant under rotations, and we can write it in this form Gij dxi dxj, where Gij has a special form, it is the identity matrix, okay. So, that is the way to generalize. Then from there to special theory of relativity, you considered 4-dimensional space, you included time as a composite 4-dimensional space, and you had the metric there as eta mu nu, which is -1 plus 1. Okay, it is a convention, plus minus also works. So, this is a 4 cross 4 matrix. So, now if you think like a sort of you like to generalize things, you may ask, can I write this in the form of this, can I generalize this quantity. This eta mu nu here is a constant. They are all the elements are constants and there are no off diagonal elements, they are all 0. You may say, okay, what happens if I make it into a general matrix G mu nu whose elements can be non-zero and they can also depend on where you are located, the place x and time, both x and t. So, and this is what Einstein did. So, then this becomes a distance, this is a generalized distance on some arbitrary space time, okay, some manifold. Okay. So, if you have this, then what is the issue that comes in? Okay. The definition of vectors, you have to be now careful. So, in flat space, when you define the vector, you set up your origin, you set up coordinate system, you have an origin, and in your mind you will probably draw lines like this and put an arrow, and the amplitude is the magnitude of the line is the strength of the vector and the arrow mark goes in the direction. And very happily you will be moving vectors around from point to point, right. When you do vector addition, a vector is here, another here, you just add them. So, when you go to curved space, you can't do that, okay, because on curved space now a vector space is defined at every point on the manifold. It is a local quantity, it is a local not quantity, it is a local structure, okay. So, the set of all vectors at every point you can have a vector space there. This is that vector which in that vector space which corresponds to it and then you compare them, okay. So, this is what is done, and because of that now you introduce the covariant derivatives are introduced, okay. So, this gives you a rule for moving a vector from one place to another. And so, the covariant derivatives, this arrow, I mean this is in flat space, the mu x mu. So, you have 4 components. The partial derivatives now becomes, there is a gamma which is the Christoffel symbol introduced here, and this is the new thing that is. So, it becomes just little bit more complicated. So, if you tell me what is gamma, I know my rule for comparing vectors. Now what is fundamental here is G mu nu, the tensor in the distance formula that I have written down. This is the fundamental thing. So, gamma is related to the derivatives of the metric tensor, and so by there are these 3. Just don't worry about how complicated it looks. We will work out in the context of cosmology, we will work out simple ones and we will see exactly what these are. So, this is the formula that relates. So, that the whole mathematical machinery of curved space is being used to write these down, to write what are the corresponding quantities you have in flat space and what are the corresponding quantities you have in curved space. Yeah. This one? Mu nu. This one? Which one is wrong? Alpha, okay. Yeah, that is correct. So, in typing, the indices are, so I have summed up alpha here, so it should be changed. Okay. Then the next thing is that the covariant derivative of G mu nu is 0. Okay. So, these are the rules that we are going to work with. Okay. So, now we are ready to write down the Einstein equation. The Einstein equation, so we have to the G mu nu, capital G mu nu tensor on the left hand side, and on the right hand side we have energy momentum tensor T mu nu. I am going to also include this constant lambda and a G mu nu, even though Einstein, when he wrote down the equation, he first added it, removed it, added it. So, we will just work with the whole thing together. Okay. So, okay. So, at this stage I just want to ask you, when you study Newton's laws, Did you derive it from anywhere? It was just given by Newton, and he said, okay, if you give it a kick, it will move like this, right. It is a law which came out of, probably he observed many things, and but if you want to derive it, did you at the later stage learn something that sort of helped you derive it? You wrote down a Lagrangian, and from that you derived it. But then who told you what is a Lagrangian? Action principle. So who told you the action principle is correct? Maybe Galileo? No. Okay. So all I want to say is that we are pushing our ignorance further and further and further. Okay. So we may feel happy that okay, we have derived it starting with the Lagrangian, but whatever I don't know, I am pushing into the Lagrangian. And then when somebody asks you who is going to tell you what Lagrangian, you write down. But there is an answer to that when you go to electrodynamics. What did you do when you wrote down the Lagrangian for the photon, mu? You wrote down a Lagrangian for in terms of f mu nu, right? And there was a condition that you use. What was that? No, Poynting vectors are gauge invariance, yes. So you make an appeal to symmetry. You say your Lagrangian should follow this particular symmetry, and then these things will follow. Now we have pushed our ignorance into what symmetry is correct. Okay. So electrodynamics came out of okay, gauge symmetry, which is one dimensional because the gauge transformation involves 1 degree of freedom. But is that the only symmetry in nature? So this questioning can go on, and this led to particle physics, SU2. So the electromagnetic theory gauge symmetry is called U1, one parameter. You go to SU2, SU3, and then you multiply their product space, and then you ask, okay, what is the Lagrangian which satisfies these symmetries? So our ignorance is now pushed into the ignorance of the symmetries. What are the symmetries that nature follows? Okay, nature chooses. So, but that's not the end of the story, clearly, right? So you can play around with so many symmetry principles, and you can see do these follow in nature. So that is the kind of thing you can do. So it is here also. Here Einstein wrote this down, but you can derive it from symmetry principle. You can write down what is the Einstein-Hilbert action. That kind of work was done later, and I'm not going to. My goal is cosmology, so I'm not going to go into that. But you can push your ignorance into that direction. Okay, that's one direction you can go to. Now let's just for the completeness of the definition, I have written down the terms which appear in the Einstein equation. So the left hand side is purely geometry of the curved space. It is given in terms of the R mu nu tensor, Riemann tensor times plus minus this Ricci scalar, and the Ricci scalar is defined in this way, contracted with G mu nu. And Riemann tensor, the R mu nu is from the curvature tensor, you can contract two of them, and the curvature tensor is derivative of the gammas. So there is a whole step by step you build up these equations, these quantities are built up in this way. So why Einstein wrote this down? Because this quantity, when you define like this, when you take covariant derivative of this, that is 0, because you want a conservation law, because you have energy density on this side, and so when you take covariant derivative, it should be 0, and that should be the conservation law. Similarly here, this lambda is a constant, G mu nu. In the previous slide, I wrote down that the covariant derivative of G mu nu is 0, and so that is satisfied. So these are the conditions which go into writing down this equation. Then another equation which is important is the geodesic equation. So on flat space, a free particle moves in a trajectory which we call it straight line. It follows a straight line, and it is given by the components of the coordinates are given by this, and that gets changed in curve space to this. So, this is the equation for a straight line. So, you can see the change is there is two time derivative. Instead of time derivative, you have a parameter which parameterizes the trajectory. You take the derivative with respect to that 2 times, and you have x mu. So, there is a 4 vector, and on the right hand side you have gamma appearing, and that whole thing should be 0. Okay. So, when you learn GR, you will be doing exercises of this. For the simplest exercise, of course, the sphere. You simplify it instead of 4-dimensional space to 2D space, and that is the usual toy example, and you can you can work them out. So, the trajectories are like the great circles, they are like straight lines on sphere. Okay, so these are the important equations, and this is a lightning move to get you to cosmology. I moved wrong direction. Okay. So, then the other thing we need is what is the stress energy tensor. So, stress energy tensor is a 4x4 matrix which contains all the information about energy, pressure, and the exchange of energy between heat flow and exchange of energy between in different directions. Okay. So, this is the quantity, and lambda is the cosmological constant, and conservation law I just now already explained to you that the covariant derivative should be 0. I think this should be mu. Okay. Okay, is that fine?
Then which components define the momentum?
So, this is the rate of change of the momentum. You take p mu and then you are taking derivative the rate at which it changes. Okay. So, the momentum change transfer, force transfer will be contained in the pressure II component. So, Tii will be if you apply a force in this direction, which is equivalent to having a momentum in that direction. If on that surface, what is the direction that is given by Pi. Okay. And these are the shear. So, if you are applying something and parallelly you are applying something, then those information are here. So, for the purpose of cosmology, we are going to drastically simplify, and we will need only rho and Pi. Okay. So, to complete the story, if we say that the Einstein equation supersedes the Newtonian equations that I summarized, you should be able to derive them from here, right, from Einstein equation. You should get them back. So, how do we get them back? One of the limits is to say the gravity is weak. Okay. Gravity is weak and static. So, that means that the G mu nu, the metric tensor G mu nu, it has x and t dependence. We drop the t dependence, it is static. And the weak means I can write it 0 0 component, and the phi phi component you can write it as x component you can write as 1 plus a small perturbation. Okay. If you do that, then we are identifying G00 with this quantity, this is G00, then you plug it into the okay, I am not go in this order, I will go here first. So, if I identify this with the potential, phi is the potential, I plug it into 0 0 equation, and you will recover the Poisson equation that we wrote down earlier. But clearly Einstein equation is, it has many more equations because it has many more components. Okay. Similarly, the geodesic equation also you can write down the rate at which something changes, the position changes of a particle under the force. Okay, so we recovered this. So, this is expected by construction. We want Newton's laws to come out from the. Now we are ready. So, those are all the very quick lightning introduction to all the equations we need. Of course, to fully understand for you, you will have to do a proper course and work out all the details and so on. That is what is needed. Now we are going to apply that formalism or the equations to study the universe, which means I am going to write down the Einstein equations to what is relevant in the universe. So the Einstein equation has many components and we do not need all of them, or let me put it the other way, it is too complicated for us to solve. You would have appreciated in the gravitational wave lecture and GR lectures that these are too complicated. So for cosmology, what we need is, let me not say need, usually physicists will simplify everything, right. You throw away everything and then simplify to a spherical cow and then you solve it. So that is what we are going to do, okay. So there is something called the cosmological principle, we talked about it yesterday, many of you raised it, and that principle says that the material in the universe should be distributed in a homogeneous and isotropic manner on large scales. So there is a rider here on large scales. Why is this put? Because clearly we see it is not the way you guys are distributed. Is it isotropic or homogeneous? No, right? There is less here and more of you there. So it is not. So on as you go to larger and larger scales, they will be homogeneous and isotropic. But there is this very fancy word principle here, which makes it sound very deep. It is deep, no doubt, but at this stage it is only an assumption. Okay? Yeah.
What is that large, like what number?
Yeah, so I will tell you, I put this picture here, yesterday's picture, to discuss that. Okay, first, so it is this principle is actually an assumption that we are making. So yesterday I showed you the galaxy distribution that Hubble plotted, okay, and at that time the data was very less, okay, and Einstein equation is too difficult to solve, so you just assume it, okay. Data cannot say whether it is really, it did look isotropic to with the large pinch of salt, Hubble's distribution looked isotropic. So it was an assumption to simplify and be able to solve Einstein's equations, okay. So that is how it started. So now to answer your questions, this is today our measurement of how matter is distributed, and you can see here that if you are the small scales, they are not isotropic, but if you average over larger and larger scales, maybe you will say, okay, the matter in this region and the matter in this region is equal, okay, equality. So people do that, there are research papers which calculate these things, and the usual ballpark number that comes out is about 100 megaparsec. Above that, then you can safely assume that it is, the distribution is isotropic. So we are really talking about very large scales. Okay, so this is today with data that we have already collected, we are able to test it, okay. But it is still it is not, no, the error bars are still large, and this is quite a hot topic of research, whether it is really isotropic or not, okay. So you will find in the literature papers dealing with using CMB data or large scale structure data. The large scale structure data can be divided into, you look at only quasars or galaxies and then you see whether it is isotropic or not. And currently there is hot debate that universe is actually not isotropic. So I will not give my judgment, but it is, people are debating it. So it is an exciting thing to study. But for my lecture today, we will proceed that this is okay, and what implication does it have on the equations. So you all know Noether's theorem. If so there is some, so this is symmetry, right? This is symmetry of translation and rotation. So that means if we apply this to the metric G mu nu, without even solving the equations, we can decrease the number of degrees of freedom, okay. And that is what is called the FLRW, Friedman-Lemaitre-Robertson-Walker metric. Oh sorry, I wrote this again, FLRW metric. So somebody asked about the coordinates, right? What coordinates are we talking about? Okay, so here I am writing down this equation without any proof, because the proof going through the proof will take a long time, but you are welcome to read through, you can read Nalika's in Nalika's book how he describes it. Okay, so let us look at this matrix. So, the general G mu nu dx mu dx nu has been written down. The G mu nu is a 4 cross 4 matrix. So, it is actually it is a symmetric matrix. So, there are 10 coordinates 10 components, and there is some other 4 symmetries. So, there are actually 6 components. So, I should have 6 equations, but 6 degrees of freedom, but here I have only 1 degree of freedom, A, and that is reduced because of the symmetry that I am imposing. Okay. Then the coordinates. So, the coordinate system chosen here, this T here is cosmic time, where you think of galaxies as far away from each other and their lines are not going to cross. So, this because this is a large scale, very large scales, and you can think of a time slice where they are all evolving together. That is the coordinate system. And here of course, this is spherical polar r theta phi coordinate system, and you notice that there is a k here which has entered into the metric form. K is a constant. The way it is derived by imposing those symmetry conditions, k is a constant, and it is called the curvature parameter, and it is normalized in such a way that it can take values 0, +1, oh I missed -1 here. So, these are the 3 allowed values. Okay. So, I am without any proof and deriving, I am asking you to accept this, okay, because yeah. It is actually not included. I am explaining to you that when you have symmetries, your degrees of freedom will decrease, and so that is why from 6 degrees of freedom of G mu nu, the counting is okay, no? So, it is a 4 cross 4 matrix, 16 minus 4, 10, and then 4 coordinate transformation symmetry. So, there are 6. Out of those 6, after imposing all the symmetry conditions, we have only 1 degree of freedom left. And there is no x dependence here, there is only time dependence. X dependence because you have isotropy. Isotropy, if there is x dependence, that means you will have vectors involved, and isotropy says there can't be vectors, only scalars will be there, and so this is the only allowed form. Okay. So let us for completeness, let us examine these 3 cases of k. So, if k is 0, then you can rewrite the metric into this equation, this form, which is just Cartesian coordinate. You can rewrite in Cartesian coordinates and you can write this. So, this is like a flat space, but with an overall expansion. A is doing the expansion with time, and this is the flat metric. The space part is flat metric, okay, and overall expansion. And so, this is the co-moving coordinate, okay. And you can also, because the equations became too many, so I did not write it down. You can also redefine the time by pulling out the A here, and overall you can have A outside and redefine time as some eta variable, and that will be conformal time, okay. So, it is a matter of choice what coordinate systems you want to work with. You can work with either of them. So, that is this case. Then the other case is k equal to 1. So, if k equal to 1 here, you can change your variable r into some sign of psi, and you can rewrite it in this form, okay. So, this form, let us, if you examine only this part, okay. So, you would have, I think you must have written the metric for sphere, at some point you must have written. So, this is like this metric for a sphere, except this d omega is the sphere metric, but there is an additional component here. So, this is like the metric on a 3-dimensional sphere, which is a subset of a 4-dimension, but it is compact. The difference is the important property is that it is a compact system, okay. It has a finite radius. Okay, so that is why it is closed. The word closed is related to the fact that it is a compact system. Yeah.
Is this substitution justified? Because while substituting R as sin psi, you automatically assume that R can't be more than 1 or less than minus 1. More than 1. So is the substitution justified?
Yeah, it is justified.
Why?
Because I am not interested in how big it is. I am only looking at the scale, the topology. Okay, I am interested in I am not really worried about the size. I am looking at the topology. But you will be worried about the size later if we think of this as a universe and it is expanding. Okay, but this is just to find out what is the topology, global topology that it has. So for that it's fine.
But like you will find the topology near the R equal to 0 case when you do substitution. The topology can have a change when it goes from -1. Like
No, topology by definition is a global quantity. Okay, so it is the global property of the entire system. If you look at a nearby local region, it will be, you can approximate it as a flat system. So similarly, the other one minus k, this is, if you substitute sine hyperbolic psi, then you will get this. And if you go in the look in the maths literature, this will be like the metric of a system having negative curvature. So can you give an example of a surface which has negative curvature? Saddle, yes. Or if you have I do not know, a bowl, this side is positive curvature, this side is negative curvature. So reverse side. Okay, there are many examples, but it is good to build the pictures in one's mind. You will find them useful in later. Okay, so this is the just by imposing the cosmological principle on large scales, this is already reduced the possible universe properties of the universe to this type. Okay, then that whatever we discussed till now will fix the left hand side of the Einstein equation. Okay. On the right hand side, the again T mu nu, because of the homogeneity and isotropy, all these terms have to be 0. So this is the equation. T mu nu has the form of a perfect fluid. So we call this a perfect fluid. All the I pressures are equal, and there is energy density in the 0,0 component. So it has only this form. Everything is scalar, and so now all we have to do is we can plug this into Einstein equation, and we can derive the equations. So let us see. So again this I am putting just for completeness. So given the metric that you had, that we wrote down, you can work out and all the formula that we have written down for the Christoffel symbol and all the curvatures. This is pure algebra, nothing to do with any concept. You can work this out and you can write this down. Okay, so pure algebra, you can work it out. So now we will plug this into the Einstein equation. So Einstein equation, again just to repeat, they will be redundant because the Einstein equation is many components, it will be redundant, and our degrees of freedom is only one, so we just need one of them. So if you actually work out, you will get many equations, and you can put it in the form which is most convenient for you. So the first equation that we will think of is the Friedmann equation, which is the A dot by A whole square. It is related to the left hand side. The rate of expansion Hubble parameter is given by the energy density rho, and the curvature term also enters here and lambda enters here. Then another equation that you can derive from the Einstein equation is the acceleration equation. So the acceleration equation gives the second derivative of A, and it has in that you have pressure entering into the equation. So this will be from Tii. So you may say, okay, if you take derivative of this and maybe use the continuity equation, you should be able to get this, right. This is supersedes this equation, but this equation is useful as a constraint. So, it's a useful equation. Then from the conservation equation, you can get the continuity equation, which tells you how the rho is preserved. So, the difference here, I wrote down the continuity equation in the Newtonian case, flat space. The difference is that here you have a Hubble parameter entering as a term here, and there is a pressure also entering, where we do not talk about pressure. There it was rho into V, okay, divergence of rho into V. So, it is changed because of the curved space, expanding curved space background. So, this is entering here.
Are we needing to calculate radiation?
Radiation of fluids.
Of universe, like we have acceleration equation and continuity equation.
Yes.
We can get intensity of the thing. And can we find radiation?
You will see what we can derive, okay. Okay. So, then, but you look at this equation, suppose I want to solve these equations. So, these are coupled equations. Again, the word background is coming here because I have ignored all the x dependence. I am only looking at the time dependent part, okay. So, to solve these equations, you have how many degrees of freedom are there? Suppose I use 2 of them. Rho is a time varying quantity, A is a time varying quantity, P is a time varying quantity. So, the equation is not closed. If you want to solve it, you need one more information about the energy density, how the rho and P are related to each other, and that is the equation of state. And we are going to work with equation of state which are constant, because in the universe that is what is important. Omega is the equation of state parameter. It relates for a given material, it relates how the pressure and the energy density are related. That is what it is. Pressure, depending on what kind of a material you have, the pressure that it exerts will depend on what kind of energy it is. So, that relation is captured in this quantity called W. So, this has to be supplied. You need that information to be able to obtain solutions for these equations. Okay. So, these are the fundamental equations of cosmology, background cosmology. Yeah. Yeah. 2 are independent, and then you need to supplement with this equation. Yeah. Okay. So, I will proceed now. Let us look at some of the solutions. Okay. So, those are quite simple equations, no, for those ordinary differential equations. You can solve them. So, I just wrote them as exercises for you. You can show that from the continuity equation, you can write rho as proportional to a to the power minus omega, minus 3 times 1 plus omega. Maybe if we have time a little bit later, you can work this out, because all the time me talking is not a good idea. You guys should also do some calculation. Okay. So, you can show this. Okay. So, this from here then the scale factor can be also, because yesterday I made a big noise about I want to know what A is as a function of time, and these equations are allowing you to obtain that. So, these are things that you can work out. Here this A can be put in this form, this is also simple, but now I ask, is this solution well defined for all W? So, you can see if W is minus 1, it will not be well defined. Okay. So, there is a problem there, and we will encounter it when we look at the age of the universe. Okay. Okay. So, more solutions. So, in the Einstein equation, the Friedman equation and acceleration equation, if I am to say that my equation of state is given by P equal to 0, okay. P is 0, that means W is 0. So, this is true for things like dust particles. So, the word people use in the context of cosmology is dust, but it does not mean it is like the dust particle. It means the galaxies, because we are looking at large scales, galaxies are like dust particles, which mean they do not exert force on each other, they are far away, and so you can take its equation of state to be 0. If you have such a, this is a toy example of course, if you have such a toy example, then from those earlier equations you can work out rho to be a to the power minus 3, and you can solve for a as a is t to the power 2 by 3. Okay. So, you can work this out easy. What you need to know is, so if I imagine the whole universe to be filled with galaxies which are far away from each other, they are behaving like that, then what this implies is that the universe is going to expand as a function of a is increasing, right. So, if you go in the future, the distances between the galaxies are going to increase. So, this is how Einstein equation, by using Einstein equation we are getting expansion as a natural consequence. Yeah.
This shows that universe is accelerating.
Not accelerating. Acceleration means you have to take derivative 2 times and it should be greater than 0. So, because of this factor 2 by 3, it will not be accelerating. Okay. So, this is decelerated expansion. It is expansion, so but it is like 2 points slowly, nicely, with time expanding. The other accelerated expansion will be 2 points, suddenly it becomes very large. So, that is the accelerated expansion. So, the second example is if the universe is filled with radiation, then you can work out that the equation of state is 1 by 3, and if you plug this in, you will find that rho goes as a to the power minus 4, and scale factor you can solve it as it goes as t to the power half. Okay. So, now you can, which one will be faster acceleration, faster expansion, sorry, not acceleration. This one will be, but it depends on at what time, right. T equal, if t is less than 1, then so these are toy examples. So, but both of these, what you are seeing is that even if universe is filled with radiation, it will still be decelerated expansion, it will not be accelerated expansion. Okay. Then if you have a universe filled with just lambda, you put the rho term to 0 and just put lambda. Here I am taking k to be 0, okay, in these solutions. You put this, then you will get the solution A goes as e to the power ht. In this case you have accelerated expansion, a double dot is greater than 0. So, these are sorry. So, yeah. It is a toy example, we are imagining, to think of this room as a universe, okay, as a compact universe, coming back to that previous K example, and you are filling this with photons, okay, in a uniform homogeneous isotropic manner. Then Einstein equation, the consequence of Einstein equation is that the space will expand. And that is the new thing about Einstein equation, we would not have got it from Newtonian physics. So, this is toy example. Of course, in the real universe we have, it is a mixture of, there is some radiation, there is some matter, and there is some lambda, and the expansion will be a consequence of all three. Okay. Maybe I will come back to this later. Okay. So, now let us come to the realistic composition of the universe. So, in the realistic universe we have the rho that enters into the equation is going to be some gamma, some baryons and dark matter. Later I will put, if I combine these two, I will just call it matter, okay, rho matter and rho lambda. So, I have to define for you what is rho lambda now. In the equation there was only lambda. So, So let me define a rho lambda which is rho by 8 pi g. So what am I doing? So I will just first define these parameters and we will go back and look at the Friedman equation. Okay. So this is defined rho lambda. I may have dropped some factors of C and all, so please excuse me for that. So rho lambda is lambda divided by 8 pi g, and you can see dimensionally it will have the same units as the other rows. So that is why we are calling it rho, but it is a constant, right. If lambda is a constant, g is a constant, so this is a constant, it does not depend on time. Then I define a quantity called a critical density, and that is, I define, it will be a function of time, 3h square by 8 pi g. Okay. So because h is depending on time, this quantity will change with time. Why am I doing this? By introducing rho lambda and rho c, let me go back to the Friedman equation I wrote down earlier. Yeah. So if I look at this here, I have h square here now on the left hand side. What I am doing is I am taking h square on this side. Okay. Yeah, I can take h square on this side and I can write this as rho divided by rho critical. Similarly, this lambda I have changed it into a rho lambda and divided by a rho critical, and I want to compare with this k by a square. Okay. So let us look at what the equation looks like now. Yeah. So this quantity omega I, this is the called the density parameter. So for every type of matter we will have a omega parameter. So this is the first place I am introducing the lambda CDM parameters. Okay. So they are the fractions of energy density of different components for every I, fraction with respect to the critical density. So then I can write down the Friedman equation in this form. Okay. This form is nice because it tells you that if this summation over, particularly this form where I have put k term on the right hand side and I on this side, you may think we are just juggling, renaming variables and juggling, but usually these are juggling. When you are a researcher, you have to think what is the best way to write your equations so that you can extract physics out of it. So this juggling is done for that purpose, and so this tells you that I am sorry, why do I have a square here? It's a typing mistake, okay. Sorry. So this should be just k, there is no square. So if I compare this omega fraction, this is the addition of all the energy components. If they add up to 1, then k is 0. So if precisely if I am able to measure and find that all these quantities, they add up to exactly 1, then I can say that the topology of the universe is going to be this flat space. Actually I should not use fully the word topology because there are other possibilities. And if it is less than 1, k will be negative. Yeah, I will just finish what I was saying, and if k is positive then it will be greater. So these left hand side is in the equations that I have written down so far, there is no way we can measure this completely, right. The equations do not tell you how to measure this, because you are solving first order differential equations, and whenever you solve equations you need initial condition. That is something you determine or you give, and then you know all the trajectory completely. So we have the equations, but we still need to input these at some time. Typically we input it at current epoch today, t equal to t0, and then we can trace back in the past that this is how it happened, because from observations we can measure them today. So with that we can tell, yeah. Sorry? Critical density, yeah. So the critical density is just by dimensional analysis I am introducing this quantity, and it is a useful quantity to compare our energy densities. Okay, it is a hypothetical quantity. It is not like a very deeply physical, from physics it is derived like that, it is not like that. It is a convenient way to introduce this. If you introduce this variable, you can, the equation becomes simple, but you can also measure, it's basically, G is a constant, we know the value, H will depend on what epoch you are looking at, it will vary with time, and particularly if H is today, if you are able to independently measure H naught today from somewhere, you can plug it in and you can say, okay, energy density, critical density, this value is this much, and whatever real energy density I have, by comparing it with that, I can say whether the universe is flat or not. So it is a convenient variable to introduce. Yeah. So it is what it is. The form is given here. Okay. But just because it has dimensions of energy, correct dimensions, we are comparing and taking it out. So in the next slide, I think I have no. Okay. Since you asked about the H before that, so let's look at that. So you can work this out. See H. So the Hubble parameter H naught today. Okay. If I were to write it as so without doing experiments, I don't know what H naught is, but let me write it as 100 times H kilometer S inverse megaparsec. The small h. Now whatever H naught unknown it is, we have pushed it into H and we have put 100 here. Again, this is just convenience. Okay, this is just, then because typically we measure H Hubble parameter to be of order 100 currently. So I mean, I need the next lecture to connect with this, but what we measure today is like there is a big fight between different groups of people, 68 or 74, so those are the typical numbers. So they are of order 100. Yeah. That's what I am trying to explain. It's instead of using H, capital H naught, we will introduce this H, because H is of order 1, small h is of order 1, because, so I am using extra additional information from observed data when I say this, that H naught today measured is like 68 or 74, around that value range. So if I were to put it in as 100 times H, this H is going to be slightly smaller than 1, and if I use 100, then I can do order of magnitude calculation. So in physics, we are not pure mathematicians, so we do a lot of order of magnitude calculations. We just plug in numbers because it helps guide our feeling, get an idea, okay, this is of size 1 meter, this is of this size. We don't need to know the precise values to develop our theories. But if we want to get exact numbers and so on, of course we need precise measurements, but we do a lot of these estimations. So for that, this is a convenient way to rewrite, because we know that the small h is going to be of that. So, so we put it like this. If you put it like this, then you can plug it in and you can show that rho c, the critical density today at T0 is going to be of this. So it gives you an order of magnitude. So you can see here, it is critical density is like 10 to the power minus 26 kg per meter cube. It's a very, very small number, no? And how will it change? When you know h precisely, the small h precisely, it will slightly change it, not too much. Because if h is like 0.7, you will have 0.7 square, it will change by 1 order of magnitude. No? So maybe it will increase by 10 to the power minus 27. So it will be in that ballpark. So that's why it is convenient to write like this. So, you should work this out. Okay. So, it is nice to see this. Also, you should work this out in terms of mass of the sun. Okay, that is another, in astrophysics people use that solar mass as a unit, because that also gives a good idea when we measure. Okay, then since we are on this page, the other thing which is useful number to get is h naught. H naught is time, h naught is inverse of time. So, you can ask how much is h naught inverse in years. Okay. So, in terms of h, without just using this, if you plug it in and you use megaparsec is this much, you can calculate how much is h naught inverse. So, when people talk in astrophysics, compare times, sometimes they will talk in gigayears, megayears. Usually in cosmology we talk in gigayears, right? You have, and so h naught gives you, because all time measurements are going to be scaled by h naught. Okay, h naught times something. So, it is good to calculate it and write it down, and the value you get is roughly this. If you plug in all these quantities, 10 to the power 9 years, it is in gigayear. And h inverse, if it is 0.7, it will be slightly more than 1 h inverse. So, maybe this will become 10. So, it becomes 10 gigayears, 10 gigayears. Okay. So, it is good to have this order of magnitude estimate. And these things you can compute. So, let me go back to the previous slide. Yeah. So, we are done with this. So, I hope this point is clear. This is a useful thing when you want to compare with experimental data. You want to, you can measure this and compare it with one, and then you can tell whether it is closed or zero, flat or whatever. Okay. Another thing that I will talk about is the age of the universe. So, again from the Friedman equation, you can do some algebraic, you can introduce the omega parameters that you have defined and scale it with. So, let me go back to the Friedman equation. Oh, I am going back. Okay. So, in the Friedman equation, what you can do, you take the square on this side, take the square root, and of course, we are interested in expansion. So, we are taking plus. So, if you are doing your calculation backward in times, you will take minus. Okay, just keep that in mind. In fact, that is why acceleration equation is nicer to work when you are general, considering both expansion and contraction. So, here if I take positive square root and I write the dt I take on the right hand side, and I bring all these quantities on the left hand side, and I express this rho is the rho total now in the realistic universe. So, there will be the capital omega terms will be there, and I plug in all their expansion rates with A. I put all of those in, and then I will have dt from here equal to h naught. This is h naught, this is I will pull out an h naught from here, Hubble parameter today. It will come there, h naught inverse and integral over all the omega terms. Okay, so that is the realistic equation that we will get. Yeah. Okay, so that is whatever I described in words in the algebra is what I am writing down here, and the rest is all simple algebra. Then for simplicity, I am introducing a variable a by a naught. So, I have not put a naught as 1, but this is usually we choose it to be 1. So, x is the variable a naught. So, the integral can be put simply, dt can be expressed in this simple form. Okay. It is just algebra, nothing very complicated. So, now you can integrate from 0 to 1, H naught is a constant, so it gets pulled out, and this is what I was just explaining to you, that any time estimation that you do will have an H naught inverse, and there will be something which depends on cosmology. When I say cosmology, I mean it depends on exactly what these values are. Unless I know these values, I will not be able to tell exactly what this number is. So, this is this is supposed to be, because I am integrating from 0 to 1, this is the formula for the age of the universe. So, now you can, so just stare at this formula. Let us consider simple cases. If you have only radiation, this is the radiation, and all of these are 0, you will be able to do the integral, right? Because there is an x here, there is an x to the power minus 2 there up, and so the integral will converge and you can compute it. And this will be typically some factor, small factor. Yeah.
Are you assuming the metric is flat?
I am not assuming anything.
I mean, while you derive the equation for A, that time you assumed the metric was flat.
No. So, the metric was used to derive the Friedmann equation. I am using the Friedmann equation to write this equation.
Yeah, but the variation.
Because there is no k here. Yes, sorry. Yeah. Okay, small k is 0. Small k I simplified it by putting it to 0. Okay. Yeah, then it becomes very long. So, also observations, these today the observational data tells us that k is most likely 0, okay, today. Okay, so that is correct. So, you can solve it. Similarly, if you have only dark matter, you can solve it. Baryon and dark matter, they are similar. So, but if you have only omega, this omega lambda, these are 0, then the integral is not going to converge, and it is, so if it is just cosmological constant filled universe, then you will not have a finite age of the universe. Yeah.
So what's the difference between what you found here versus the exercise you found?
Exercise, is it this one?
We got -9
Yeah. So, well, that exercise is supposed to be related to this exercise, to what I just described, age of the universe. This number we know, this number, where this number, okay, the age of H naught inverse is like this one here, 10 gigayears. So, that is useful to already get an idea what this number is going to be. This is going to give you 10 gigayears, then there will be some contribution from here. So, when you work this out, there will be some number that you will get. So, this is the remaining part of the exercises. You take this example, simple cases where it's only this or only this or only this. This one you will get infinity, but this two you will get some number, and that number will multiply this, and that tells you the age of the universe. So, that exercise is to give you the order of magnitude estimation. Okay, so far so good, right? Okay, then another variable that we will that people use a lot is, you want to know, you do not want to go all the way up to a equal to 0, but you want to know up to some point what is the age of the, how much time has elapsed, and that is usually called the look back time, and that you can express in terms of, maybe you can say, okay, at redshift this, how much time was, what was the age of the universe at that time, or measure from us how much time was it in the past. So, that also you can do, that I am rewriting the equations in terms of redshift, okay, because in the formula you had A. So, that A you convert into redshift, and you can place it like this, and this is something you can all calculate and store it in your, you can calculate it numerically and store it, use maybe Python to do it. Okay. So, you can at a given, if somebody gives you a redshift, you can calculate how much time it has been since that time to today. Okay, so I think for this lecture, this is my last slide. So now these are what I spoke in words, these are the exercises, it's good for you to do this computation. So I will close here, and okay, I will close with this slide. Yeah, I think this is the slide that I want to close. Oh. Okay, so this slide is summarizing all the things that we have studied. Let's look at the first plot. The first plot, we did not talk about this. Okay, so this is time. So yesterday I said that I want to know how is A behaving as a function of time. Maybe I should have put this first. Okay, let's look at this first. And this axis is don't take the values very seriously, because it's hard to get the correct in this unit, it's hard to get the whole thing to fit. So so you know that because time A is a monotonous function of t, you can replace your equations and rewrite it in terms of A. So you can think of A as a time variable. If I do that, we saw how matter, gamma, lambda, they behave as a function of A. Then so here, if I compare this to, this one decreases faster than this. Okay, so and this one is constant. So if today I measure that this is the one which is dominant, which is the purple one. Okay, so this magenta line is the one, so this is, we are here today, magenta line is the one dominant here. Then if I go back in the past, because in the past this is constant, this one would be the one which is dominant, it will increase, because in the past it is increasing. But if I go back further back in the past, there will come a time when this one will be larger. It has, regardless of, I am not carefully putting the proportionality constants. The proportionality constants will depend on what those omega fractions that we measure today, because I have not told you what those numbers are. That is why I am keeping it as just proportional, but we know that this should have happened. And so the important epochs are now, so there is a matter and radiation equality epoch, so that is an important epoch. And if I look at that epoch, that in my drawing here A is a function of t, it is drawn in this regime. So in this regime here A will go as t to the power 2 by 3, right, we worked that out earlier. A goes as t to the power 2 by 3 if it is filled with just matter, galaxies. So in this region it will be like t to the power 2 by 3. Here there should have been a radiation domination era. That means because this row green color is dominating, this era will be somewhere here, and that will be t to the power half. So if you, my figure is not clearly telling what are the slopes, so just take the picture with a pinch of salt and you try to draw it correctly for yourself. Okay. So we have basically, in what I have described today, till today we have covered this region, this epoch, and we have not covered actually the present epoch because we need more observational data for that, and we have not covered this epoch. So I hope to cover them in the next lecture, okay, say something about those. Okay. So let us pause here. So I have skipped many important things because I have only few hours. Okay. So in the next lecture I hope to tell you about how to fix those, use observation to tell what those omegas are, and also about a little bit about the fluctuations. Okay, let's go for tea.
surprisingly, the age of the universe is like the h naught inverse, right?
Yeah.
And then that particular integral. So when you put the small h as 0.7
Yeah.
in order to get 70 megakilometer per second, actually the t naught itself gives around 13.9 billion years. So basically, it's coincidentally that t naught is basically h naught inverse.
Yeah, with small corrections from the